Hello. This is the second exercise, the canned version of the lecture for the second exercise. I'm Dr. Atkinson, Dean Atkinson. I'm going to be walking through some background information on how to construct a Rovibrational spectra, such as you would find in spectra taken by FDIR instruments or scanning IR instruments. You'll remember, hopefully, from physical chemistry that that type of spectrum is generated or primarily probes the vibrational motion of molecules. So we will be thinking about vibrations, but we'll also be thinking about rotational degrees of freedom. So a lot of the information content that we got last time in exercise 1 will carry over into exercise 2, and in fact there will be a nice opportunity to use exercise 1 as a template for building exercise 2 spreadsheet. This is the second exercise that uses Excel. Again, we're kind of starting with Excel because we think you have quite a bit of familiarity with working with Excel, and it's relatively easy to work with. It has some severe shortcomings, as you probably appreciate after exercise 1, and some of those same problems come back to plague us here in exercise 2. But nonetheless, we will go ahead and finish using Excel, and then we'll move on to a different type of programming language next week and the week after that. So again, this class is all about the fact that you can do all kinds of interesting mathematical problems with a whole host of different types of software, different programs, without spending too much time learning how to use the program. So without further ado, we'll go ahead and start talking about Rovibrational spectroscopy. And the reason it's called Rovibrational is because there's both rotational and vibrational spectroscopy going on. I'll back up a step in just a second and show you the bigger picture, which is electronic is also possibly involved. And after that, we'll focus back in on Rovibrational spectroscopy. So I've got a little cartoon of a diatomic molecule here that I've drawn ahead of time to save you from having to watch me draw it in real time. Again, vibrational spectroscopy refers to the fact that this bond may be elongating and shrinking, similar to the two balls on a spring, and that's the primary motion that we'll be talking about. But we have to keep in mind that it will also be rotating just like it did in the last exercise, and so we probably should add on a degree of freedom that shows the molecule tumbling around its axis or around the center of mass, so to be completely complete. So the spectrum that we'll be getting this time is similar to the spectrum that we got last time, and so I've drawn a picture of a pretty badly drawn idealized picture of what a Rovibrational spectrum sometimes looks like. And so again, we have individual lines similar to what we had before. We've illustrated the fact that these lines have some width rather than just being sticks, have different probabilities or intensities associated with them. And if you've had the third term of PChem, you can appreciate the fact that there's actually three types of information going on here, or three different branches is what I'm referring to. So this set of transitions down here comes from one type of rotational transition within the vibrational manifolds. This type, or this peak, comes from a different type, and this type set of peaks comes from a third type. So I've actually labeled the energy axis this time, or the x-axis in this case I've labeled energy, and we will work in wave numbers on this exercise. So if you switched everything over to megahertz or gigahertz last time, you'll want to change your units back to wave numbers for this exercise, because that's what's used in vibrational spectroscopy. And so since we know that these set of peaks here is the highest energy and this set of peaks is the lowest energy, those of you who have had PChem will know that this is the R branch and this is the P branch. But we'll get to that in just a second for those of you who haven't had it. So this is pretty much what we're looking for in real molecules. Some of them, or actually a very large number of diatomic molecules, do not show a Q branch. So that's the one in the middle. And as the exercise points out, there's a real simple way of dropping in sort of a conditional variable that allows you to shut that off if you want to compare to a real experimental spectrum. So you can make it to where you can turn off that Q branch so it doesn't interfere with the rest of the information if you want to do that. And the other thing to keep in mind is that if you ever did want to compare to a real spectrum of a real molecule, you'd have to choose a molecule with a dipole moment, because these IR spectra are only recordable for molecules with dipole moments. Raman spectra can be taken of molecules without dipole moments, but that's probably not as easy to lay your hands on. Okay, so we will go ahead and go on to the next slide here. We may hop back to take a quick look at this when we get there. But again, we need to show energy levels. That's sort of the starting place always in spectroscopy, and so we're going to use cartoon versions of energy levels similar to what we did last time. And we'll start off with our generic energy axis going up, as we almost always do in quantum mechanics and spectroscopy. And so again, we're going to start showing some energy levels, and I'm going to draw a slightly different cartoon than I drew last time. And so this cartoon that I'm going to draw, hopefully, again, is familiar to some of you, and it's what's called a potential energy surface. So this drawing that I just made, this swooping diagram, is basically a plot of energy versus R, and I'm just going to put two dots here, two circles, to imply that it's the R, which is the distance between the two atoms in your molecule, in your diatomic molecule. And so this potential energy surface implies that being out here at very large internuclear distance, very large separation between the two atoms, is not as good. Remember, in potential energy, down is good, is not as good as being here where the two atoms are separated by some predefined distance. And again, basically what we've illustrated here is a chemical bond. So the bonded atoms are better than the non-bonded atoms. And then the other thing to keep in mind is that when you move the atoms too close together, they start to run into one another. That's a bad description of what happens, but basically the electrons start to repel one another very dramatically, and you'll hit a very sharp inner wall where the potential energy goes up very fast. So the picture that we've drawn basically tells you an awful lot about a diatomic molecule. Again, it's an idealized picture for diatomic molecules only. If you wanted to go to a polyatomic system, this coordinate would be replicated in many different dimensions. So drawing multidimensional pictures is beyond my artistic capability. The next thing that we're taught to always do on these diagrams is to put that line in there. And the reason that we're supposed to put that line in is because that thing that I've just drawn here is the first vibrational state of the molecule. So in fact, molecules are not allowed to be at the bottom of this well. They're only allowed to be in one of the vibrational levels. We talked about this last time. Quantum mechanics says you can't be anywhere in between the vibrational levels, and the lowest vibrational level is that line I just drew, and that line is not at the bottom of the well. And if you remember back to physics, this difference between the bottom of the well and this first vibrational state is referred to as 0-point energy, and that's some energy that's locked up in all molecules, so it's not really accessible to chemical reactions or anything like that. So I'll draw a couple more of the energy levels that we're talking about this week, or this time, depending on when you're watching this. So these would be individual vibrational levels within this potential energy surface that describes a molecule, a diatomic molecule. So again, the diatomic molecule can be in V equals 0, it can be in V equals 1, it can be in V equals 2, it can be in V equals 3. So again, we come up with a quantum number, and the quantum number that we're dealing with this time is V. So it's a V quantum number, and we'll go ahead and label those states as we just talked about. So there's the 0 state, and the 1 state, and the 2 state, and the 3 state, and I'll just kind of move those into the right places there. So 0, 1, 2, 3. Okay, And one of the interesting things that you can kind of tell from looking at this diagram is that when you're in the V=3 state, you actually are moving further in the internuclear space, in the R coordinate, to these extremes than you were down here in V=0. And that kind of makes sense. When you put energy into vibrations, the molecule actually vibrates more energetically and the atoms move a greater distance. So that kind of makes sense. Then I'm going to skip some space, and I'm going to suggest that way up here at the very top of the molecule, something slightly different happens. And so things start to move a little bit closer together. So one of the hallmarks, again, of vibrational spectroscopy or vibrational treatment of quantum mechanics, and this comes from the harmonic oscillator model, which those of you who had the third term of PChem would remember, is that the energy levels for vibrations are supposed to be spaced about the same amount. So the difference between 0 and 1 is about the same as the difference between 1 and 2. That stops being true way up at the very top of the well, where the states actually move quite a bit closer together. Maybe this is 56 and 57 or something, depending on how well you draw this diagram. These very high-lying vibrational levels start to move very close together. And the extreme, of course, is the molecule vibrates enough that the two atoms go flying apart from one another and end up as separated atoms. So this is referred to as the dissociation limit. So this is where you put enough energy into the molecule, it actually vibrates enough that it blows itself apart. So kind of interesting, and we'll come back to that in exercise 8, where we'll actually simulate that type of motion, find out how much energy is associated with breaking bonds, and also map this potential energy well using Spartan program and come up with where, come up with the fit to the surface, the harmonic oscillator fit, which in principle would allow you to calculate where these levels are. And then we'll also fit it to this sort of strange form that has this elongated edge out here, which is referred to as a Morse oscillator. So get a chance to see both of those fits. And again, if you know how to use Spartan and you're keen to get going on that exercise, feel free to jump ahead in the schedule and do that one at some point, rather than having everybody trying to use the 8 licenses on the 8 computers that we have that has Spartan at the very end of the term. So one last thing I thought I would illustrate before I go on to the subject matter of this week's experiment is what it would look like if you did the next level up. And so I'm just going to make a little break in the axis here and suggest that there's a whole bunch of energy in between this surface that I drew and this other surface that I'm going to draw. And so I'm going to draw it, and again, I'm a bad artist. But one of the things that I'm trying to emphasize here, and I'll put my lowest energy state in here again, one of the things that I'm trying to emphasize with this drawing up top is that it doesn't necessarily have the same bottom of the well position as this one does. And if you think about it for a minute, that kind of makes sense, because sometimes the upper electronic state, so this one up here is a different electronic state than this one down here, sometimes the upper electronic states have different bond orders. So let's say this bond is actually half as strong as this bond. Went from a bond order of 1 to a bond order of a half, or maybe a bond order of 2 to 1.5, or something like that. So basically what happens is the internuclear distance changes because the bond order is different. The bonding that holds the two atoms together is different. So kind of an interesting part of the story, but not really where we're headed today, so I'll leave it at that and skip back down to the levels down here. So again, we've got 2 different electronic states that we're showing. We've got a number of different vibrational states within the ground electronic state that we're showing. And then the tricky part is every one of those individual vibrational states that we drew, V=0, V=1, V=2, has the whole collection of J states, rotational states built on top of it that we showed last time. So if we took those individual states and blew one of them up, so let's say we're just looking at V=0, we would have V=0, J=0. We would have V=0, J=1, J=2, J=3, J=4, and so on. So there's a V equals 0 version of it, and there's a V equals 1 version of it, and a V equals 2 version of it. So these are all the J states that we talked about last time. So again, you get to transfer everything you learned last time onto this diagram. And now, instead of just having transitions between J states, we can also get transitions between V states. Okay, so as we did last time, we have to come up with a selection rule that tells us which of the transitions are allowed. So again, we drew a diagram here that implies that all of these individual vibrational states are the same distance from one another, 0 to 1, 1 to 2, 2 to 3, and so forth. So we can draw arrows, and we can think about which arrows are allowed and which arrows are not allowed. And again, we can draw an arrow from V equals 0 to V equals 1, and we can also draw an arrow from V equals 0 to V equals 2. Okay, now a little bit of terminology here. This state, or this transition V equals 0 to V equals 1, is allowed. So the selection rule for vibrational spectroscopy is pretty much similar as the selection rule for rotational spectroscopy. So delta V equals 1. And in this case, we're talking absorption, so I'm just going to talk about delta V equals plus 1 is allowed. So delta V equals 1 is okay. The delta V equals 2 that I've drawn here, sorry, get the right tool here, this one here, is not allowed. Now, in the context of vibrational spectroscopy, it's not as strongly disallowed as it is in rotational spectroscopy. So you will sometimes see evidence of these transitions, and they're referred to as overtones. So this transition is referred to as a fundamental. This transition is referred to as an overtone. And in fact, if you look very, very close, you will see these. So again, you know, one of the things, if you haven't already picked up on it in chemistry, allowed means you're going to see it. Forbidden generally means you're only going to see it if you look hard. So forbidden, sometimes I joke, means strongly discouraged. So those overtone transitions, even though they're forbidden, actually will show up. But in the context of this experiment, we're going to ignore that V equals 0 to 2 because we don't expect it to be very strong. And so we're going to cross that out. So put a little X through it. And we expect we will see the V equals 0 to V equals 1. And then we also theoretically think we would see the V equals 1 to V equals 2, and the V equals 2 to V equals 3. And that makes us think a little bit, well, if I should be able to see the 0, 1, and the 1, 2, and the 2, 3, and they're all sort of at the same energy, wouldn't I either see only one spectrum from all those different vibrational transitions, or would I see spectra that were just slightly offset from one another? And the answer is no, you don't see any of the other ones except for V equals 0 to V equals 1. And the reason that you don't typically see anything but V equals 0 to V equals 1 has to do with our old friend, the Boltzmann equation. So one of the calculations that you will do is a Boltzmann calculation that is not on the J states this time, but is on the V states. And what we'll find is that the difference between these two vibrational levels, and I should have been careful about this little arrow that I drew off to the side here, because what I meant when I said, you know, the rotational levels are built onto the vibrational levels and drew this little arrow over here, is I meant this is like times 1,000 or something. You have to really take a close look to see the individual rotational levels within the context of the vibrational levels, which are much, much farther apart from one another. So again, if we set V equals 0 and J equals 0 to be equal to the 0 in energy, and we calculate the energy difference associated with V equals 0 to V equals 1, how do we find that out? Well, again, we're given a formula that relates the vibrational state V to the energy of the state. So again, we can create a level in our spreadsheet that goes V equals 0, 1, 2, 3 if we want. But then we can also calculate the energy associated with that transition, and we will need parameters, and the parameters in this case are omega E and omega E XE, and they're both given in that in the write-up for the lab. And again, we will consult our old friend, the NIST Chemistry Webbook, and it will tell us what those omega E and omega E XE values are. And again, make sure that you're at the very bottom of that table. And, you know, go to the constants of the diatomic molecules, go way down to the bottom, make sure you're in the X state, the lowest electronic state and grab those values of omega E, Xe, omega E, and also alpha E, beta E, and gamma E, if you can grab all of those. Some molecules, they're available, some of them are not. In any case, when you do the calculation, you will find that the difference between these two states is very large, thousands of wave numbers typically, hundreds to thousands of wave numbers, whereas these differences were usually 1 or 2 wave numbers, or maybe even less than that, depending on which molecule you chose. So what's going to happen is that when you calculate the population difference between these two states, you're going to find that 99.99999% of the molecules are in V equals 0, and 0.000001% of them are in V equals 1 or something silly like that. And what that means is we don't have to pay attention to any molecules that start in any state other than V equals 0. So in reality, when you're looking at Rovibrational spectra, you're almost always, absorption spectra, I should be careful about that, you're almost always looking at transitions out of the fundamental state, or out of the ground state, out of the V equals 0 state, into the other states. There are types of spectra that you can record that show higher lying vibrational transitions, and those are called hot band spectra. And it's pretty much exactly what it sounds like. You heat the molecules up to 100 or 1,000 degrees Celsius, and that pushes them into higher vibrational states, and then you can see the transitions out of those higher vibrational states. But again, you know, if you start off at room temperature and you start with an average diatomic molecule, the only thing you're going to have at the beginning of the experiment is V equals 0, and you're only going to see transitions to V equals 1. So really, there's only one vibrational transition that we need to pay attention to. So going back to the page before, the whole spectrum that I showed, let's see if I can find out, there's the button. So this whole spectrum is one vibrational transition, delta V equals 1, going from V equals 0 to V equals 1. So that's the whole story. And then the question becomes, well, geez, why is there 3 different types of transitions? Well, let's go back to our picture here, and we may have to refine our picture a little bit. So let's say that this set of levels here, and I won't label every J level because we already did that last time, and that's good enough for us. So let's say this is the V equals 0 set of J states, so V equals 0, J, V equals 0, J equals 0, V equals 0, J equals 1, so on and so forth. And then let's make another stack, and we will, again, not pay attention to the fact that V equals 0 and V equals 1 are actually quite a bit different from one another. So I'm going to put a line through here, and I'm going to suggest that we could start the V equals 1 state right here. And so this is going to be the V equals 1 state, and the V equals 1 state, you know, of course, is separated by a whole bunch of distance from the V equals 0 state. And I'm not trying to make the differences between the J levels that much different. I'm just not very good at drawing this. All of our population at the beginning of the experiment, and let me put a label on that top one just to keep things clear. So this is V equals 1 up top. So all of our population is down here in V equals 0 in these different J states, and it's distributed amongst the J states exactly like it was before. So the same Maxwell-Boltzmann distribution that we calculated last time says how much is in J equals 0, J equals 1, J equals 2, J equals 3, so on and so forth. Okay, not any of it is in V equals 1, so none of these states are originally occupied. We're going to go from V equals 0 to V equals 1, so that's the transition that we're talking about. But we also have to go from some J state to some other J state, and that's where the P, Q, and R come in. So it turns out that you are allowed to do 3 different types of transitions when you do this change. So the selection rules are delta V equals 1 and delta J equals 0 or plus or minus 1. So we're allowed to do 3 different types of transitions. Now that's where it gets a little fuzzy, because sometimes you are allowed to do the delta J equals 0 transition and sometimes you're not. But for the sake of this exercise, we'll assume you can. And then if, like I said, if you want to be really clever, you can build it into where you can turn off the ones that are delta J equals 0, which is the Q branch. So some molecules allow J equals 0, some do not. Some allow delta J equals 0, some of them do not. Some only allow plus and minus 1. Okay, so those are our selection rules, and we can draw some of those transitions. So starting in v equals 0, we can go from v equals 0 of the, v equals 0, j equals 0 to v equals 1, j equals 0, and that transition involved no change in the rotational quantum number. So it went from one change in v but no change in j, and the ones that have no change in j are labeled q. So the q, and then the other part of the label for rotational lines within rovibrational spectroscopy is to put the level that they started on. So q0 means it went from one v level to another v level, so v equals 0 to v equals 1, but did not change j, and it started off on j equals 0. So the next one that we could draw, that's almost exactly, that's very analogous, is, nix that one because I did a bad job of drawing here. So the next one we could draw, that's similar to that one, is the one that goes from v equals 0, j equals 1 to v equals 1, j equals 1, and that would be q1. So those are possible for all the different v states, so we could draw all the individual q's. The next thing that we could draw is a transition that had a delta j equals 1. So we'll start on v equals 0, j equals 0, and we will go to v equals 1, j equals 1. So change of v of 1, change of j of 1. So j equals 0 to j equals 1. That's an R line. So R lines are the ones that correspond to delta j equals 1. And this one started off in 0, the state 0, so it is R0. So the R0 line goes from here to here. The R1 line would start in 1 and go to j equals 2 in the upper state, so on and so forth. Okay, so I bet you can guess the P transitions. They obviously go down in j by 1. And to get a P transition to happen, you can't start in 0 because there's no way to go down below 0 in the upper state. So the first transition that you can show that is a P transition has to start in j equals 1 and go to j equals 0 in the upper state. So this one here is labeled P1. Okay, so we have transitions that involve a change in V but not a change in J, and those are labeled Q transitions. They're always labeled with the state they started off in, the J state that they started off in. We have R transitions that involve a change of J of +1, so they involve a delta V of 1 and a delta J of 1, and again they're labeled with whatever state they started in. And then we have P transitions that involve going from V equals 0 to V equals 1, but losing 1 J in the process. So of those three transitions, you're thinking to yourself, which one of them is the biggest? Well, obviously the biggest is the one that gained a V and the J. So in terms of energy space, the R's are always bigger than either of the other two types of transitions. So just to hop back here, we can throw a label on this thing that says these ones up here must be the R transitions, and we kind of can tell from looking at the diagram that it's the lowest R is here, the R0 and the R1 and the R2 and R3 and R4. So they get bigger as we go in that direction. Then we, since we're here, we take a quick look at this Q peak, and I've drawn the Q peak kind of strange. I've drawn it in kind of a distorted way where it doesn't look quite like the other ones. Why is that? Well, if you take a look at it, every one of these transitions goes from V equals 0 to V equals 1, but doesn't change J, and the J's distribution, the energy states in the upper state, or sorry, in the lower state and in the upper state are actually fairly similar. They will change a little bit. The B values will be slightly different for this state versus this state, so you do actually have to create a set of J levels with a different B up here. But the difference is not very big. And so you will have basically a whole bunch of transitions that really are going up in V but not up in J very much, and so they, well, yeah, the J part of it isn't changing very much, and so all of these Q transitions are going to be at about the same energy, which means they're very nearly degenerate, which means they stack up, and so they give rise to a fairly big peak, but not very good differentiation between all the individual little peaks that live underneath the big peak. Okay. So the last one is the Ps. The Ps are at lower energy, and they fan out quite nicely. And the last thing that I should point out is that it is possible, because of the difference in Bs between the two states and the difference in Ds, for you to stop going up in energy or stop going down in energy. So going back to this diagram, the R's in this case look like they're getting further apart, whereas the P's look like they're getting closer together. And it's possible that they stop and turn around and come back the other direction. So let me kind of say, and then they start coming back this way. And if they do that, that's referred to as a band head. And the band head refers to the fact that this entire spectrum, the R, the P, put labels on these, P and Q. So R, P, and Q all together, one vibrational transition is referred to as a band. So this whole assortment is referred to as a band. Each of the individual pieces of the band are referred to as a branch. So this is the R branch, the Q branch, and the P branch. And every one of these things is still referred to as a line. So these are lines within a branch within a band. So that's the terminology. That's the jargony piece of all of it. Okay. So again, R is bigger than P for sure. Q's are in the middle. The hallmark of Q's is that they're all very similar to one another, have a tendency to lay on top of one another, and generally one or the other of R and P gets further apart from one another, whereas the other one tends to get a little bit closer together. And you'll see this when you actually do the simulations for molecules, and it's kind of fun to see. Okay. So calculating the energy states is very similar to what you did last time. In fact, you can use the same setup as last time. Calculating the upper states a little bit different because you have to use a different B and a different D, so you probably just copy and make different columns for those two within your spreadsheet. Calculating the population, again, you only have to calculate the population for the ground state, so you can calculate all those populations. In fact, you may just be able to use the populations that you calculated last time. And then the tricky part is when you actually start putting together transitions, you have different types of transitions. Of course, you have R transitions and P transitions and Q transitions. So what I'm going to suggest is that you actually make 3 tabs in your spreadsheet. So make separate tabs for the Q, the R, and the P, or make them in one tab and then expand out into 2 tabs, because the last thing you're going to have to do, of course, is that every one of these transitions coupled with a population that's based on the lower state is just going to give you a line. So again, just like last time, what you're going to end up with instead of these nice spectra is a bunch of sticks. The sticks give you the wavelength position, the height of the sticks gives you the, the height of the sticks is based on the population, the Boltzmann population. And to make the sticks into the peaks, you're going to have to do exactly what you did last time. You're going to have to simulate the peak as a Gaussian. So again, I recommend using the norm dist function. If you remember last time, that involved sort of flipping the data on its side and creating all those Gaussians and then putting all the Gaussians back together at the very end of the experiment. If you split things out into the P, Q, and R, not only do you not have to keep track of 3 times as much data in one tab, but when you actually make the graph, you can make a graph that shows the P lines as a different series from the Q lines, as a different series from the R lines, which is kind of cool. I mean, it gives you a chance to use different colors for the 3 different types of transitions. Okay, so the basic idea is to take the stuff that we learned last time, push it a little bit further to simulate what's going on with the vibrational transitions, use a lot of the stuff that we built last time, and come up with a spectrum that's actually, something similar to what you might see in the lab. And in fact, if you've done PCAM Lab 444 already, you will have actually taken the spectrum of HCl, which looks pretty much like the spectrum, except it doesn't have a Q branch. And so if you have your hands on that old HCl spectrum, you can actually compare it to your measured, your modeled spectrum and see what you get. But I don't want everybody to simulate HCl. That would be kind of boring. So I would recommend that you try whichever molecule you're interested in. And the NIST website, the NIST chemistry website, has a whole bunch of IR spectra. So it's very likely that you'll be able to pull out the gas phase IR spectrum and compare it to it. It's tough to actually compare quantitatively. So what you probably do is just put pictures of the two things next to one another and say, yeah, it kind of looks like it's the same. It's at about the same energy positions, and it roughly simulates the other spectra. As you did last time, when you make the Boltzmann distribution, so basically these stick spectra, you can play around with temperature, so you can see the effect of temperature on the different branches, the R branch, the P branch, and the Q branch. And again, one of the things I hope you take away from this exercise is that the vibrational states difference are a whole lot larger than the rotational state differences. And so you really don't expect to see a whole lot of population in V=1, and that's why we don't expect to see a whole doubling of all of these lines from V=1. Okay, that's about all I have for today. If you obviously, if you have any questions, you can come by and see me, or go and see Jimmy for help on the programming exercises. And of course, we'll also probably try and do a live version of this if you prefer to actually be able to ask questions as you're going along. Thanks again for your attention.